Okay, this part is about how scientists work in the scientific method. So what we need to remember is that the scientific method is an organized process used by scientists to answer our questions. It is made up of a series of typical steps, and what that does is it allows the experiment to be replicated, which is just a fancy word for the term repeated, or combined with the work of others. It also allows collaboration among scientists. In other words, it allows them to work together in different parts of the world. So what we're going to do is we're actually going to go through the different steps of the scientific method. So step 1 is stating the problem. And when we state the problem, we use observations to identify a problem you want to explore. Stating the problem is usually in the form of a question. Step 2 is forming a hypothesis. This has to be a testable solution to the problem or question that we created in step 1. It should not be in the form of a question. It must be in the form of a statement. In fact, it must be an if-then statement in order for it to be correct. Step 3 is to set up a controlled experiment to actually test the hypothesis. And this consists of a number of different things. You need to list the materials that you're going to need. You create a list of numbered steps. That is called your procedure that will be followed. You identify the variables in the experiment. Specifically, you are going to identify the independent variable. This is the variable that gets changed by the experimenter. And your textbook may call it the manipulated variable. It means the same thing. The second variable is the dependent variable. This is the variable that gets changed because of the change in the independent variable. This is the one that you don't have to do anything to change as the experimenter. For instance, if I'm doing an experiment with plants and I want to see how water affects its plant growth, the amount of water that the plants receive, is the independent variable. I control that. The dependent variable is how much the plant grows. I can measure the height of that. I can't force that to happen more or less. It just happens all by itself. The third type of variable are the controlled variables. These are all other variables that we have to work very hard to make sure are the same. So for instance, with the plant experiment, I would need to make sure that all the plants were the same type and about the same age. They also would have to receive the same amount of light, grow in the same size pots with about the same amount of soil. As you can see, there's a number of others that could potentially have to be controlled as well. So that's why sometimes it can get difficult. We need to set up at least 2 groups to test. The first one is the experimental group. This one is the group that has its independent variable changed from normal. The second group is the control group. This is the group that exists under normal conditions, and we need that in order to compare our experimental group results to see if there is actually a change. Sometimes we will, with the control group, we see a change from normal, and that's what we refer to as the placebo effect. It's kind of like, sometimes you feel better when you think you're taking medicine and it turns out that all you really did was take a Tic Tac or something like that. You're not really taking anything better to make you better, but for whatever reason, it kind of tricks your mind into making you better. And we do see this happen a lot of times, with humans especially. You also need to include safety precautions. If there are no specific safety information that you need to include, then you need to recommend general laboratory safety rules. For instance, like wearing your safety goggles, washing your hands, that sort of thing. You need to identify the data that needs to be collected, including when and how. How should include any equipment that would be being used, and when needs to be very specific, because a lot of times in experiments you can't undo a step that you just did. Lastly, with this step, you need to identify a way to improve how reliable or valid that data is. Easy way to do that is to run it again or repeat it X number of times, or to increase the number of experimental subjects that are going through the original test. For instance, if I'm running a test and I run it on 10 subjects, a way to improve my data would actually be to run it on 100 at once. Step 4 is recording and analyzing your data. Data should always be recorded in a data table. And when we analyze data, we are trying to find patterns and connections within the data, and this involves the construction of graphs. We are going to be going over graphing as part of our next unit. I know some of you have probably already done graphing, either as part of math or science, but we will review it so that we can make sure everybody is on the same page. Step 5, drawing a conclusion. What you have to be careful of is this is not a summary. This should not tell me what you just did in your procedure. We already know what you did. That's not what I want to see. Okay? A conclusion needs to be unbiased. So in other words, it needs to be free of what we call bias. And let's just define quickly what bias is. Bias is when the result is swayed by what you expect to see. So it's kind of like thinking that you see it or drawing a very thin line between it that really probably doesn't exist. So in other words, seeing only what you want to see. When you draw your conclusion, you need to reference any patterns, if any, that you see in your data. You're also going to refer back to your hypothesis and tell us whether or not it was supported and explain why or why not. You need to be specific using your data. The one word I don't ever want to hear you use is the word prove, because we are not proving anything with these experiments. We're only running them one time. That's not enough to prove anything, right or wrong. What you're going to do is either support it or reject it. If your hypothesis is not supported, you could propose a revised hypothesis that you would test with a different experiment. You don't have to outline the entire experiment, but you just need to say, this would be the hypothesis I would test further or next time. Step 6 is reporting your findings. You would thoroughly and neatly write up all the information from steps 1 through 5 and submit the report. For scientists, they actually work to get their work published in several scientific magazines or journals. For you, you need to thoroughly and neatly and completely write up your information and submit it to me. Now, on the handout that you received, you'll see a nice summary here of the scientific method. Okay, this goes through the steps that we talked about, and it shows how this is actually a continuous loop. After the conclusion, the no means I have not supported my hypothesis, so that means I can discard it or change it, and I loop back and try again. If my hypothesis is supported, especially if I've tried it many, many times and it's supported, I can develop a law or theory, which would be the end, or it could generate even a new question, which could start the process all over again. Now, sometimes in the course of experimenting, we need to use scientific models. And I guess the question is why? Why would we want to use a model? Well, a model, first of all, you need to remember is that's a representation that makes it easier to understand things that might be too difficult to observe directly. So some examples of models are things like physical models, like a physical model of an atom or DNA molecule. We can't actually see anything that small, so we make it our size so that we can see it, manipulate it, and understand it. Conceptual models, graphic models like maps. You use those in social studies all the time. Conceptual models, like the one we just looked at with the flow chart. That's a conceptual model. It's a diagram. It's also a verbal description. So they have a place. If we're looking at something that maybe affects the whole Earth, that's a little too big. So we need to actually bring it down to scale so that we can examine it more easily. Solar system is another great example. I'm sure several of you in here made models of solar systems, coming up through science in the elementary and the middle school. You can't really study the solar system as a whole. We can't physically visit each planet, but we can actually look at them in terms of their size and scale with a proper model. Now, this section I actually want to end talking about 3 words that often get confused in science: belief, theory, and law. So let's start with belief. A belief is an assumption we make about the world that we expect to be true. In other words, how we think things really are. An example I use with this is a little kid. They believe in Santa Claus. They think Santa Claus is real, that he visits every single house, if you've been good enough, on Christmas Eve. That is their reality. They really think that that is how things are. But as we know, that's not always the case. A scientific theory is a step up, or sometimes we just call it a theory. This is a well-tested explanation for a series of observations or experimental results. They are based on repeated tests, and the more tests that we have or have conducted, the stronger our theory is. Theories, though, can be revised. So as you can see by this definition, because of the repeated testing and the evidence, we actually, theory in science is very, very strong. You also have to keep in mind that it is an explanation. So it's explaining why something happens. The confusion with this word comes into play simply because when we are not in the science realm, we use theory in a very different way. When we talk about having a theory about something, oftentimes we're guessing. But remember, in science, that guess is a hypothesis. It is not a theory. Scientific law is the last one, and this is a statement that summarizes a pattern in nature that seems to be true all of the time. It explains what happens. It doesn't explain the why. For instance, we will be dealing with Newton's laws of motion. One of them says, for every action, there is an equal and opposite reaction. That's telling what happens. It doesn't explain why. That's the job of a theory. And there are several examples of that. We have gas laws that we work with, and that you will work with in chemistry. But those are laws. Scientific laws are as close to scientific fact as we will ever get. We can't say 100% for sure that it's a fact, because while it seems to be true all of the time, it doesn't necessarily mean that at some point it won't be.